Hi everyone, this is the second video on the gravitational fields topic for A-level physics. This video covers Kepler's laws, including the derivation of the third law. We will also look at satellite motion, specifically geostationary satellites and the link between orbital height and speed. If you want to get the free PDF presentation and question sheet for this topic, along with lots of other resources, click on the link in the description below. Enjoy the video. Let's look at Kepler's laws. So check with your specification to see which of these three you need to know. In my experience, all exam boards expect you to know the third law and be able to use this relationship here, and we'll come on to that one. But other exam boards may or may not expect you to know the first and the second. So the first law is a statement that orbital paths are elliptical, by which we mean this squashed circle. So this is true of orbits. And if we're trying to describe those, then this is the second law. So this is a statement, and we can talk about what it means in a moment. As a planet moves in its orbit, a line from the sun to the planet sweeps out equal areas in equal time. So this is going to move around the planet around this ellipse, and it's going to move more slowly as it's further away and more quickly as it gets closer. So we end up with this particular arrangement of geometry. So the area of these green segments are equal as it moves along its orbital path, because it's moving more quickly when it's closer to the sun and more slowly when it's far away. And we can actually explain this in terms of conservation of energy, because as the planet is further away, it has a larger gravitational potential energy and therefore a smaller kinetic energy. As the planet moves closer to the sun, it moves more quickly. And we looked at that in the previous lesson about lower orbital heights have a higher velocity. So we've got a greater kinetic energy and we've also got a lower GPE. So energy is conserved. So this statement is a little bit technical, it's a little bit counterintuitive. And if this is on your specification, then you will need to learn it. The third law, and this is the one we're going to focus in on, is the time period squared is proportional to the mean distance cubed. So we can write this as t squared is proportional to r cubed. What that means is, if we look at all the planets in the solar system, I've just got 4 here, and we consider their time period squared and their distance from the center of the sun cubed, then we get a proportional relationship. That's a straight line through the origin. Most exam boards will expect you to derive this expression and actually derive the formula. So this is what we're going to do now. So first of all, we need to consider that the centripetal force, if we're talking about a planet, is provided by the gravitational force of attraction. So we have mv squared over r, centripetal force, is equal to the gravitational force. So we could simplify at this point, but I'm going to simplify later on. But if we look at this expression here, then we've got mvr and we've got gmmr. So we want to get rid of the v. So we're going to assume that we have a circular path, which contradicts Kepler's first law. But this is the way we do it. So it's moving in a circular path, so constant velocity or constant speed, v equals s over t, where s is the circumference of our circle. So we've got v is equal to 2 pi r over the time period. So instead of writing v on the left-hand side here, we're going to write 2 pi r all squared, which is 4 pi squared r squared, divided by t, which is our t squared, and we have the m and the r from previously. So now we can tidy this up. So we've got a little m, we can get rid of that. We've got an r squared and an r, that gives us an r on the top. R squared gives us r cubed. And I think that's all tidied up. So we can make t the subject, so bring the t squared from the bottom to the top. So t squared is equal to 4 pi squared over g m, big M, r cubed. So this is our algebraic derivation of Kepler's third law. The t squared is proportional to r cubed. Now, if you prefer, you could write this constant on the other side, in which case it will be the reciprocal. So that will be gm over 4 pi squared on the left-hand side, multiplied by t squared is equal to r cubed. So you can write this as you prefer. So let's have a look at an example. So we've got the mean orbital radius of Jupiter orbiting the Sun is this value here, and we assume that is between the center of masses. We're given the mass of the sun and calculate the orbital time period. Okay, so we should have everything. We know big G, we're given that. We know big M is the mass of the sun. We don't need the mass of Jupiter in this case. And we're given the time period. No, we're trying to find the time period. We're given the value of R. So we need to make, first of all, T the subject. So that's going to be the square root of all of this. And then it should just be substitution. But there's a lot going on here in our substitution. So good calculator technique is very, very important. So we have 4 pi squared on the top. That's straightforward. We've got big G here, multiplied by big M, which is the mass of the sun. That's the object in the middle. And we've also got R cubed on the bottom. So watch out for kilometers. So we've got 7, 7, 8, 10 to the 6 kilometers multiplied by 1,000 to think of as meters. And then we have our cubed operation there. And you should work out, don't forget to square root. This is a really common mistake in the exam. And you should get 3.73 10 to the 8. Now be careful, because a lot of students miss out on an easy extra mark here because they leave the answer in seconds, and the question is specified it wants the answer in Earth years as opposed to the years of other planets. So we need to divide by the number of seconds in 1 year, which you should be able to do. So that's just 60 times 60 times 24 times 365, and we get this value here. So we would certainly expect it to be larger than an Earth year, and Jupiter's not that far out, so yeah, a little bit larger. That sounds about right. Right, geostationary satellites. So most exam boards will expect you to be able to describe what these are and also use Kepler's third law to calculate the height, which we will do later. So let's look at what the definition is, and then we'll just talk about that. So they orbit the Earth at the same rate, by which we mean the angular velocity. So be careful, they don't have the same speed, but they have the same angular velocity. They have a time period of 24 hours. So this is really important, because if you look up from any position on the surface of the Earth, then in the sky, whether it's the day or night, the satellite will always appear to be in a fixed position relative to the Earth, which is why they're called geostationary. They are very much not stationary, they're moving at thousands of meters per second. But from our point of view, they are stationary. Now, the only position this will work is over the equator. So if we imagine this satellite rotating or orbiting, it must be above an orbital position above the equator. If we try to get it orbiting the poles or any other position, then this would not work. Now that might be geosynchronous, and that's another type of orbit, but geostationary must be above the equator. And the reason why we have these, if you're asked why we have geostationary or what they are used for, is for telecommunications. So this is TV, radio, etc. And the reason why is because satellite transmitters and receivers only need to point in one direction in the sky. So we don't need a complex, expensive, and rather messy tracking system where you have a satellite tracking an orbit as it moves in its position across the sky. So these are really useful. They're quite expensive to put in orbit and maintain in that position, because as we'll see, it's quite a high orbit, but they're used a lot. There'll be hundreds, if not thousands, of these things orbiting above the equator. So our standard question is calculate the height. So where is this orbit? So we're going to use Kepler's third, and we're going to make R the subject. So we're going to have to find the cube root. But before we do that, we need to know what the time period is. And this very often confuses students because they think, well, I don't know what it is, I'm not given this value. So we need to understand that by definition, a geostationary satellite has a time period of 24 hours. So we just need to convert that into seconds. So the number of seconds in 1 day, 60 times 60 times 24, is this value here. And you should be quite familiar with this, and you should be able to recognize that if it's provided in the question. So we need to rearrange this expression here to make R the subject. So it's going to be the cube root of t squared multiplied by gm all over 4 pi squared. So we've got our value of t, and we're going to square that, multiplied by g multiplied by m, divided by 4 pi squared, and then it's the cube root of all of that, and we get this value here. Now at this point, it's quite useful, because if we've been asked to find the height, just to think about what we found here, that's the distance from the center of the Earth all the way to the satellite. And that's not the value we're asked for in the question. We want the height. So we need to subtract the radius of the Earth. So if we put this value here into kilometers and we can subtract the radius of the Earth, 6,400, we get effectively 36,000, just slightly less than that. So if we compare that to the Earth's radius, it's approximately 6 times the value of the Earth's radius. That is quite a large or quite a high orbit, which is why it's quite expensive to get the satellite into this position and maintain its position. One more thing to consider with satellites is the relationship between velocity and orbital height. So we've already said that the centripetal force is provided by the gravitational force of attraction, and we use this starting point here to derive Kepler's third law. So what we could do is tidy this up a little bit, because we've got little m, we can get rid of that, and we can get rid of one of the r values, and then make v the subject. So this is quite a useful expression, which may or may not be given in your formula booklet. It varies between exam boards. So the orbital velocity, satellite velocity, is equal to root g big M over r. Now you may be asked to show or explain why satellite velocity is greater in a lower orbit. So this is definitely the case. If you have a relatively high orbit, then the satellite velocity will be relatively low. But in order for this to remain in orbit, if we have a lower Earth orbit, then we have a much greater speed. So this is quite an important relationship to derive, and sometimes this is something we need to do in the exam, and this might be 3 marks in the exam. So you might be asked to derive this expression. If you're given it in the formula booklet, you might just need to be able to identify it and then talk about what's happening. So g and m are constants, and we have r on the bottom, and we can see that a smaller radius, if we divide by a smaller value, that leads to a larger velocity. So it's not inverse proportional, it's actually an inverse square relationship, but certainly mathematically, the smaller the value of r, of height, the bigger the value of velocity. So that's quite a useful thing to consider. That is the end of lesson 2 on gravitational fields. So if you haven't done so already, then do have a look at the circular motion videos on YouTube. And as always, you have all the first year topics available there, and the year 2 topics will be available soon. If you want more detailed support with your A-level physics learning, go to payhip.com Grade A Physics, where you'll find a whole range of really fantastic resources to improve your understanding. See you next time.